Let's pick up where we left off. All right. So some recap questions. Those in gray, we haven't gotten through them yet. Look at them later when we're done. Define a sampling plan. Who would like to define what sampling plan means or entails? As much of it as you can remember. You don't have to have the complete answer. Sammy. So everything that Sammy listed, which we probably could not hear, all of it, I'm going to go back. Where is it? Where do I have it? Did I just pass it? Okay, sampling. So sample size, meaning how many samples we need to collect to be representative of the whole lot. What kind of sampling procedure we need to use to collect these samples. How are we going to prepare them and preserve them until analysis so that we don't change composition or characteristics of the sample, as well as during transportation. So if the samples are being prepared, pulled from one plant and then going to be analyzed in your laboratory somewhere else, how they should be transported so that we don't get differences in the composition. Okay. Why is sampling plan important? Laura?
If you don't have a good sample, you don't have a good plan, then all your data is going to be accurate.
Exactly. So basically, it's the most important integral part of the entire process of food analysis, because if we mess it up from there, from the beginning, we cannot trust any of our data. So we have to do it right, so whatever we analyze, we can trust and make good decisions. What is attribute sampling? Michelle?
Attribute, it's checking for presence or absence of a variable to determine if it's acceptable.
Yes, checking of specific component that is not randomly distributed, or that is randomly distributed, not normally distributed. That means it can be in any location in the food. So it's not homogeneously distributed in your food. Whereas variable sampling, William?
It's normally distributed and usually there.
So it's normally distributed, it's there, so you take a small set of samples to determine that variable attribute. Okay. So the size, that means how many samples we put out or how many sets of samples we put out, is really dependent on our purpose. What do we want to look at overall quality? What would be sampling cost? What is the objective of the analysis? So many different variables. But if we are doing analysis for certain component that is regulated by the government, like nutrition labeling, we have to follow what the way they wanted us to do it. So the specific sample size is dictated by that agency. So, for example, the FDA and FSIS for nutrition labeling require composite sampling, and I'll talk about this later. But composite sampling, it means that they require you pull out 12 samples randomly from your population, at least 12 samples, and you combine them, hence the composite sampling. So you combine them, and then from there you take 6 replications. So this is required by these agencies. Okay. So in order to accept a lot or reject a certain lot, so you go by obviously sampling, and there are different sampling sizes. So you go with single sampling plan. That means you take one set of samples from your population. That means N is for the number of samples you pull out, and C is for the number of units that are defective. So how many samples are defective? So based on what is allowable, so maybe you're allowed to have 5 defects in the samples that you pull out, then if they are less than 5 defects, then you accept. If they're more, then you reject. Double sampling, that means you take 2 sets of samples, set 1 and set 2, and then you look at number of defects, and then you determine, based on the number of defects in the 2 sets of samples, you determine whether to accept or reject. Multiple is an extension of double, so you take multiple sets of samples, and then based on the number of defects, you accept or reject. So the complexity, or whether you decide for single, double, or multiple, it depends on the risk of accepting a lot versus the risk of rejecting a lot. And that I'll talk about later, because you don't want to risk accepting a lot, for example, that has health consequences, that you really want to be very careful in doing multiple sampling or even sequential sampling. I'll talk about. If it's just a matter of consistency and quality, and you are really being consistent, and it's not something that you're going to risk the health of the consumer, you might going to say, okay, single set of sampling, if it passed, then we're all good. So sequential sampling is an extension of multiple sampling, and it is in a sense that you take a set of samples. Let's say you take a set of samples with 40 individual sample that you pull out, like 40 cans, for example, from the lot. And then you look at certain defects in the can. Let's say we're looking at particular defect. If there is a hole in the container, there's oxygen that went in or something like that. So if you have 40 samples and you found 1 or 2 defective samples, you just accept and stop sampling. But if you pulled out, let's say 30 samples and you found 8 defects, you just reject. If you take 20 samples and you found 2 defects, you continue sampling. So it is a more extensive type of sampling, but again, it really depends on the risk for accepting or risk of rejecting your sample. So here's an illustration. If it says, so you have your population, you take out a set of sample. If it is below a certain defect number, you accept it right away. If it's above a number that you stated that this is the maximum defects we can have, you reject right away. If it's in between, you take another sample and again test the defects and then count the defects, add them up, and compare them to a minimum accepted and a maximum accepted.
I have a question.
Yeah, of course.
I think I understood on the previous slide when
On the previous slide?
yes, the middle part that you when did it take a second sample?
So if the number of defects is between an acceptable and the maximum acceptable. So if it's in the middle range, then you take another set of samples. So in case of looking at mycotoxins specifically, which one of these is correct? Remember, participation was worth 2 points. So if you know the answer, or you think you know the answer, don't hesitate. Even if it's wrong, that's fine. Okay? A and C. And?
How does the A and C?
Amanda? A is correct, C is correct. So A and C. So because mycotoxin is an attribute that is not normally distributed, so you might have fungal growth on certain area of the food or in the lot. So it won't be distributed equally or normally within your sample. So you want to make sure you take out a lot of samples to ensure that you don't have mycotoxins. Obviously, it's not single sampling plan, because if you take one set of samples and you don't find mycotoxins, it doesn't mean that mycotoxin is not available somewhere else or present somewhere else. And if you make an error, a sampling error, the impact of an error in sampling is much greater than the impact of your analytical error. And again, if you sample incorrectly, you might make a decision that could be harmful for the consumer, or may cost you, if there is no mycotoxin, might cost you a lot of money to reject.
When we're talking about like the acceptance sampling, will it usually be referred to as like single acceptance sampling plan, or will it be like single sampling plan?
Say that again.
So you're talking about the acceptance sampling and
Yeah.
like single, double,
Yeah.
and all that. So will it, when it's talking about that kind of plan, will it be like single acceptance sampling plan? Because I guess I read B and I thought like a sampling plan is the big overarching.
A single single acceptance sampling plan. Yeah.
Okay. So,
Oh, that, yeah, I see where you're confusing. I should have said single acceptance. So that,
it'll normally be written with acceptance.
yes,
Okay.
unless I mess up. So you can ask me like you just did. Okay. Yes, Anna?
What would be like an example of a single acceptance sampling?
Yeah, there are so many different situations where you have that. But let's say you're looking at a quality parameter that does not endanger your or have a high risk, and you know that you've been consistent in it for many weeks. Let's say you're looking for total solid content, okay? And then you just measure it and you know that you've been consistent. There's no high risk in making a wrong decision. Any other questions? Yes, yes, Sam. Say that again.
Would you be able to choose like a different sampling plan for like food components?
Yes, that's a very good question. Depending on what we're analyzing, whether we're analyzing mycotoxins in the same sample or we're analyzing moisture content of the same sample, sampling plan will be different. Yes. Okay, so the risks, here's where we have to think about the risk when we actually plan our sampling, whether size or the entire plan. We have what is known as consumer risk. That means this is really important because it impacts the consumer, whether from a health perspective or whether they're going to like your product and come back and buy it, or then you would lose your consumers or lose your customer. So, but most importantly, it's related to health. You do not want to accept a product or a lot that might have high implications on the consumer. So when you make a decision, you want to make sure that the consumer risk is less than 5%. Less than 5% of you accepting a poor quality population. There's also the vendor risk, because also you don't want to reject a lot that is potentially good quality and you just rejected it, because that causes you cost. It costs you money. You lose money that way. So there is always also that risk, but it is higher. There is more leeway to that, 5% to 10% of the lots. Overall, you want to be reasonable in your sampling plan. You want to think about time, efficiency, cost, all of that. So you want to make it as simple and as flexible as possible when you make your decisions. You want to protect both the consumers and the vendor, and you want to ensure that your results are true, are reliable, you can trust them. So this is an example of sampling procedure. So within the sampling plan, after size, we think about, okay, we determined how many samples we're going to pick out. Now, how do we pull out these samples? This is a simple example of flour sampling. This is an official method for sampling flour from AOAC. In this case, let's say you are a flour mill and you're producing bags and bags of flour, and you want to test certain quality of that flour. So how are we going to do it? You're producing, let's say, in simple terms, 100 sacks of 50 pounds flour, but you're producing much more than that. If you're producing 100 sacks or big 50 pounds of flour bag, you take the square root of that number, which would be 10 in this case, and then you take samples from 10 bags randomly instead of measuring everything. So from these 10 bags, the way you pull out sample, you pull out 2 samples potentially from the throwing sample from the corner diagonal to the center. So if this is the center, so you go to this corner, or this corner, or this corner, or this corner. And you draw a second sample from another corner. You take these samples and you store them properly under sealed, in a sealed container in dry and clean conditions. So when you have a homogeneous sample, like a homogenized or mixed or stirred oil, so it's a homogeneous sample. So wherever you pull your sample of oil, it's going to be fine. It can be taken from any location. But sometimes you have a heterogeneous sample product. So let's say a truck full load of potatoes. Each potato is different. One might have mold on it, another might not have mold on it. So you really want to look at taking from multiple locations from that truck that is full of potatoes. So you have manual sampling, which is prone to human error. Usually it's done by experienced personnel, and you can use different tools to take out samples. This is an example of a core sampler. And you can have mechanical sampling, which is less biased, and it is for, let's say, in line of processing. You want to take a milk sample. So it would be, there would be a mechanical installation of a unit that would, after a certain number of minutes or hours, a sample is pulled for analysis to look at fat content after producing what you think is low-fat milk. So you want to make sure that you defatted the milk and you produce a 2% milk. So you, at certain time points, you would pick up a sample and do an IR on it to determine the fat content.
Is that
Carrie?
Yes. Is there a case where manual sampling will be preferred over mechanical sampling?
Yeah, mechanical sampling is not always feasible and present in your facility. Then you would have an experienced personnel online that would, not necessarily online too, it could be after production, so you would have to have a personnel that knows what they're doing when they're doing the sampling. So there are two types of sampling, non-probability sampling and probability sampling. Probability sampling is obviously preferred, but when you have situations where you cannot do probability sampling, such as when you have a container full of grains, so you really don't have the option to be able to randomly select samples, statistically select samples. So you rely on judgment sampling by an experienced personnel that would know where and how to take a sample. It is biased, obviously, based on the person. Sometimes it's restricted sampling, so you have this huge silo and you can only reach the top. You cannot really get a sample from the bottom. So that is, this is what you have and this is what you take. But many times you're able to do probability sampling when you are producing products such as canned food or individually packaged products, bags, packages, cans. So you are able to do probability sampling. In this case, you follow something we call random sampling. That means if you are producing a huge number of cans, obviously, an example, a lot of cans per lot, and of course you want to select a certain number of cans, let's say for nutrition labeling, so you're going to do 12 cans from this lot. So how do you select these 12 cans is by random sampling. So you get a random table of numbers, you number your cans, and then you select randomly, close your eyes and pick a number, 12 different samples, 12 different numbers. So that would be a randomly selected set of samples to be analyzed. Okay. Systematic sampling, that is similar to when you have a mechanical sampling online. Every an hour, every 2 hours, the sample is automatically withdrawn for analysis. That is systematic sampling, no human bias, it just goes by timing when a sample is pulled for analysis. Stratified sampling, this applies to if it's a company and they have multiple plants. So a company is producing tomato soup, tomato paste, or what have you. So, and they need to test their production for consistent quality across different plants. So each plant will be, you would stratify, so you would divide your population based on the number of plants you have, and from each plant you apply random sampling for each plant. So random sampling is within stratified sampling, and this is for when you have multiple plants producing the same thing by the same company. Cluster sampling is similar to stratified, so you stratify, you divide your population across the different plants. But in this case, instead of sampling from each plant, you randomly select which plants to test. And each time you select different plants. The composite sampling is the example I gave you for the government regulation, FDA and FSIS, for nutrition labeling, where you take 12 samples randomly from your lot, and you combine them, mix them well, homogenize them well, and from there you take 6 subsamples for analysis, or 6 replications. Which of these do you consider as potential problems associated with sampling that will result in reduced Jason? Yeah, yes, all of the above. Definitely, whenever you don't have a statistical way of picking up samples, you have due to convenience or restricted access, yes, this will be associated with reliability issues. For storage conditions, it's going to impact the composition of your sample. And yes, flavoring, obviously, that's a big blunder. So consideration when you prepare your samples. So now you have selected the number of samples, you have selected the way you're going to sample them, now you have to prepare them for analysis. So you want to have as much of a surface area as possible to enhance the accuracy of your determination. So oftentimes you have to reduce the particle size of your sample. So this is an example I give every year. I walked in one time on a capstone group trying to determine fat content in a potato chips. So they were doing that by using a Muginer assay, where there is a digestion tube, and you put your sample usually, and then you put your, after the sample is digested, you just put it in there. I don't think they even digested the sample now that I think about it. And then you mix it with solvent to extract the fat. And I walked in and I found a whole potato chip in that flask. Like, what are you doing? Extracting fat. No, you're not extracting fat. You did not reduce the sample size or the particle size to allow for efficient extraction of the oil. So you really need to reduce your particle size, and often there is a recommendation for the size of particles. So if you're doing general approximate analysis, 20 mesh, and we talked about that last time. Mesh number is the number of openings or square openings per linear inch. And then the higher the number, meaning you have more opening, meaning you get smaller particle size. And usually they recommend a smaller particle size when doing extraction assays, because you want to increase the surface area as much as possible. Now there are cautions when you want to grind your sample and make it homogeneous. Sometimes your sample is moist, or it's sticky, or something that does not allow regular dry grinding that we use. You put your sample in your grinder and you grind it. But if you have high moisture, sticky, high fat, it's not going to work well for you, especially that because then you lose moisture, or moisture will prevent it from being homogeneously ground. And if you have fat, you lose some of the fat, will stick on the sides. So you cannot do regular grinding. So the solution would be cryo-grinding. That means you freeze your sample. You can freeze it with nitrogen, or you can put it in the freezer. Or you can freeze it with CO2, right, Cindy? The dry ice. Liquid nitrogen. We don't do it with dry ice? Yeah. Okay. Pour liquid nitrogen on top of it, and then it freezes and becomes solid. And then yeah. Oh, and sometimes we use it. I remember now. If you freeze it with liquid nitrogen in the grinder, you can put a couple of pieces of dry ice to keep it solid throughout the grinding process too. And who doesn't know what dry ice is? Huh? What is dry ice? It's okay if you don't know, if you haven't heard it before. It's not a very common thing. Well, it's common for us, but what is dry ice? Say that again. The solid version of CO2. How do you make CO2 solid? What do you do usually for gas to become solid? Compress it. So we do a lot of pressure, right? To compress and make it, you can make CO2 into liquid, and you can make CO2 into, so you change the temperature and you change the pressure to bring that gas into a solid phase. Okay, just explain everything there. So while we're preparing the sample, one other thing I forgot to mention is we always have to also be careful when we are grinding your sample is not to overheat. Some grinders can heat up a little bit, and heating up your sample can result in losing moisture, for instance, or initiating reactions that you don't want, side reactions that you don't want with high heat. So sometimes we tell the student, okay, let it grind for a minute, stop, wait, and let it grind again. Another issue is metal contamination. So depending on the grinder you're using, where you put your samples in, especially if you're measuring ash or iron content or what have you, you don't want contamination from other material that you use. And then once you grind your sample, you filter the sample or run it through sieves that you can ensure these mesh numbers are reached. And there are certain ways you can do physical, using a sieve physically, and you put your sample on and just shake your sample through. Or there are tools like the rototap that has different compartments with different sieve numbers, and then you can utilize that to separate particles based on their particle size. All right, the last thing here, during sample preparation or storage, we want to eliminate enzyme or control enzymatic reaction. We talked about that as of why. Why we want to ensure no enzymatic reactions? Said that earlier. Yes, Hayden?
So that it doesn't change the product.
Yes, so it doesn't change our product. So you don't change the fat content by breaking the fats into different components and then they get oxidized, or breaking the proteins up, or hydrolyzing anything you don't want it to be hydrolyzed. How do we control it though? Sam?
Control you stop the enzymes from.
Yeah, how do you stop the enzyme?
Freeze them, keep them very.
Yes, so you can store your sample. If you know that your sample is high in enzyme, store it under cool condition. You can freeze it, you stop the reaction with enzyme. Or you can begin.
Maybe enzyme is sensitive to pH.
Yes.
Your product can endure the heat and the acid.
Yes, definitely. So you can change the pH if the pH is not going to impact anything else. If you can reduce the pH to an acidic pH, for instance, some enzyme will be inhibited. Sammy?
This is a dumb question, but if you were gonna test it on the shelf life, wouldn't you want local enzyme activity to happen with your product?
That is not a dumb question. That is an excellent question. Yes. So if you are measuring shelf life, you don't want to inhibit anything because your mode of failure could be very well your lipase activity or like oxygenase activity. So you definitely don't want to do that. That is an excellent question. Good. Another way to eliminate enzymes, if you want to eliminate the enzyme, is by heat. You can denature the enzyme if whatever you're going to test is not impacted by change in heat or temperature. We want to avoid lipid oxidation, obviously, because this is going to change the characteristics. How do we avoid lipid oxidation? Paul? Yes, we can add antioxidants. Excellent. What other thing we can do that is very simple? Yes, Tia? Put it in a vacuum, yes. Put it in a vacuum or flush with nitrogen so that you can remove the oxygen and the nitrogen replaces the oxygen in your head space of your storage container. Very good. Antioxidant, flush with nitrogen under vacuum. Seal it well. Put it away from light if you are worried about photooxidation. Limit microbial growth. Why do we want to limit microbial growth? Adele? Yes, well, spoilage, but what would spoilage do? Change the composition. Your microbes are going to ferment and eat up some of your constituents. You don't want that. Change the pH, change the sugar into acids. It's going to just mess up things for you. Okay, how do we control microbial growth? What? Controlling the temperature of storage, right? So we can store it in refrigerator or freezer. What else can we do? Sam?
Proper sealing.
Proper sealing, Birgitta?
And control the water moisture.
Control water moisture. What else? But sometimes the water moisture is present in your food. You can't do much about it. Oh. What's that? Yeah, you can control pH level. Another thing I was looking for is you can add chemical preservatives to prevent the growth of microorganisms. So, any measure you want to avoid alteration of your sample. Yes, Adam.
So, to control
other microbes? You don't want to add any microbes because microbes will ferment, will grow, so they will be eating on something. And then who will live? Somebody's going to live. It's the life for the fittest or whatever is that quote. Somebody's going to be fit and will grow. And like how they grow is they're going to eat up your food. Good though. All right, so here's an extra credit option. So what you have here is this question comes from your study question for chapter 5. if you solve it and bring it to me on Monday, you get +5, not +2. So if you want that +5, which will come in really handy on your quiz and test, go ahead and solve that problem. Okay, I have 30 minutes to start a new lecture. What? What did you say?
It's not right.
What? Oh! A for effort. A for effort. If you put effort, but it's wrong, you'll get the credit. If you put one sentence and no effort, yeah, you'll get a 0. Okay, you are a very energetic group. I leave you for 1 second and you start talking. You're very energetic. Last year they were silence in the room. When I want them to talk, they don't talk. This group is very energetic. I like that. Okay. This chapter or this lecture is very important, not just for this course, for later on, if you ever work in any research field where you need to run analyses or run methods for any, whether for R&D or typical analytical, you will be preparing the agents. Okay. And sometimes buffers as well. So what we're going to learn today is how do we do that? We're going, in order to learn how to prepare agents and buffers and solutions of different dilutions, we're going to have to remember certain equations that you have for sure taken in the past, whether in high school chemistry or the intro chemistry you take here at the university. So you know that it's not first exposure, but I'm going to remind you of them and how we use them to prepare the agents, different diluted solutions, and buffers. So we will go over a lot of different exercises, calculations, and the associated lab is not next week, the week after. There will be a lot of calculations as well. We won't leave you until you know how to do these things. So you'll give you a lot of examples to work on. Okay, so what do we know about buffers? It's okay if you don't know the answer. What?
It's a solution that will keep the pH stable no matter what you do, no matter what you add.
Perfect. Based on your answer, what's the right answer here, Paul? A and C. Yes. So it stabilizes a certain pH. It maintains a pH, but that pH doesn't have to be neutral. We have buffers that maintain acidic pH. We have buffers that maintain alkaline pH. And a buffer, it is a mixture of weak acid and conjugate base. In order to stabilize the pH, your buffer, meaning how it works, it has components that either picks up hydrogen ions, or we call protons, or they give hydrogen ions. So when they pick up or give hydrogen ions, that means they are resisting the change in pH. So let's think about it as titrating. If we're titrating with acid and you have a buffer in there, so when you're titrating with acid, that is, you're giving H plus to the system, you're giving protons to the system. Your conjugate base is going to pick up those protons. So there is something that will buffer. Instead of having the pH go down, the conjugate base is going to pick up that proton, and you don't see a change in the pH. On the other hand, if you have a buffer and you are titrating with NOH, a base, so you're giving OH minus. So what happens is your weak acid is going to give up a proton to neutralize the presence of OH minus. Then the pH remains constant. So these two have specific roles to absorb protons or give protons in a way to maintain your pH where you want it to be. Under what circumstances we want to maintain a pH? In an enzymatic reaction. Oh, sorry. Go. I didn't see you.
Oh, it's okay.
Yes. So, yeah.
In our own blood.
Yeah. You went deep there. Outside the body.
Well, I mean,
Jason,
I could.
are you going to give me a meat example?
Exactly.
Okay, I know it, Jason.
No problem. Because it kind of has to do with blood, but yeah, and the fact that you don't want pork that's pale and gets really acidic.
So do you add buffer to your steak?
A buffer.
To the steak?
To the steak, no, it's just that it's called pre-harvest.
No, I know what you're saying. You're right. There are certain situations where you don't want the pH to change. That is a correct answer. I think what I want to clarify is my question is, when do you need a buffer? Or when do you need to work when there is a buffer in your system? And that's when I started saying when you are doing an enzymatic hydrolysis, for example, or running an enzymatic assay, you want to maintain the pH of the system to the optimum of that enzyme, for example. So you want to make sure that you have that buffer maintained. In which experiment, I'm blanking right now, which experiment do we use a buffer for in analysis? Do we have any experiment, or we just prepare a buffer for them, for example? Where do we use the buffer? I'm blanking. I don't know if we use it in analysis.
We have
Oh yeah, that's when we actually measure organic acids with our buffer. Yeah, but a good example I can give you is the when we run enzymatic reaction and you want to maintain the pH of the system. Okay. What is wrong with B? Yes, I was saying that the buffer doesn't have to be neutral, doesn't have to be pH 7. You have buffers that are pH 3.6, acidic buffers, okay? Maintains an acidic pH, so it doesn't have to be neutral. So the buffer may be neutral pH, but it doesn't have to be. Yeah, it just maintains one pH. Doesn't matter what the pH is. Okay. All right. That's the fun stuff to remember. Okay, different forms of concentrations. You're going to encounter all of these forms of concentrations throughout the lab. So I want you to remember what they are because you'll be working with them the entire semester. Molarity is number of moles per liter of a solution. That's the unit of molarity. And number of moles is defined by the mass of your reagent or chemical by the molecular weight. And the molecular weight is the mass per 1 mole. Okay? When we say the molecular weight of any compound, it's weight per 1 mole in grams. Okay. Normality is the number of mole equivalent of the solute. Getting a little bit more complex here. Mole equivalent of the solute per liter of solution. And what we mean by mole equivalent, if it is an acid-base reaction, it's the easiest, is how many hydrogens we have or how many hydroxyls we have. So, for instance, you have H2SO4, sulfuric acid, you have 2 hydrogens. So that means you have 2 mole equivalents. So the number of mole equivalent is 2. When you have HCl, is hydrofluoric acid, 1 proton, your number of mole equivalent is 1. If it's not acid-base, it would be the electrons transfer during a chemical reaction. So that would be the number of moles equivalent of the solute. So 1 mole of HCl equals equivalent to 1 normal of HCl. HCl because you have one hydrogen. Whereas H2SO4 you have two hydrogens, so number or normality equal number of moles equivalent times the molarity. So because you have two, this here two, so normality is twice the molarity. Okay, so 2 normal of H2SO4 is equivalent to 1 molar of H2SO4. Okay? This comes in handy when we want to determine the concentration of our organic acids. Some organic acids have 1 carboxyl group, that means they give up 1 hydrogen. Other organic acids have 2, others have 3. So when we calculate and we want to determine the percentage of our organic acid, we take into account in the equation the number of mole equivalents. We'll get to that when we get to that chapter. But I just want you to remember that this is in terms of how many hydrogens you have in an acid, how many hydroxyls you have in a base, or how many electrons are transferred within a chemical reaction. Equivalent weight is simply the molecular weight per number of mole equivalent. So instead of the regular molecular weight, which is mass per 1 mole, here it's mass per number of moles of equivalent. So the equivalent weight of H2SO4 is 98 grams pi 2, which is the number of mole equivalents, is 49. Again, this is relevant when we calculate organic acid concentration, especially the organic acids that do have more than 1 carboxyl group. We'll get back to this again later on in the semester. So hold that thought, remember, for later. Percent concentration, oftentimes we prepare our reagents or solutions in a percentage. Means how many grams per 100 milliliter or how many milliliters per 100 milliliters. So it could be weight by volume or volume by volume, excuse me, or weight by weight. The last, before I let you go, is when concentration is much smaller than 1%. So we will encounter ppm, parts per million. We will encounter this concentration in our atomic absorption lab where concentrations of minerals are really low. So parts per million is equivalent to milligrams per kilogram or milligrams per liter, or micrograms per milliliter, that is parts per million, or parts per billion, or parts per trillion. So it can go as low, infinitely as low. Okay, we will continue on Monday. Have a great weekend. I posted what you need for next lab on Canvas.